Hey everyone, this is Shikhar Kwatra. I am going to show you my Capstone project as part of this Coursera course on advanced data science. As you can see my screen, I have uploaded the architectural decision document over here. We are going to skip that and I'll directly jump over to my main code, which has all the information pertaining to the dataset and how I trained the dataset in order to come to specific conclusion. As you can see on this GitHub link, I have provided all the relevant Python files relevant for this course. As part of our machine learning platform, I used Watson data platform where I created all these files, which are data exploration, ETL, feature engineering, model definition, model evaluate, and training the model. Let me go ahead into Watson Studio and show you the dataset first. So I gathered this dataset from a website online and it consists of 51 sensor values. All of them are float sensor values, and it also consists of null data, NaN values as well. So it is a dirty dataset which I am trying to tackle. The overall goal is to try to predict the machine status based on the certain set of these sensor values. So we want to correlate the sensor data in order to identify whether the machine status would be normal at a particular point of time, or it would be in recovering zone, or the status would be broken. So that's the main goal. And it's a time series based pattern. So you can see that we have timestamps over here as well. Let me go ahead, go back to the Capstone project. And let's start off with data exploration over here. So you can see I imported all the relevant libraries for this particular, for training the particular model. And I'm using specifically pandas and scikit-learn as part of the training. So you can see initially I started off with data frame and copied the original I copied the CSV file into this data frame, and I have all these set of sensor values along with the machine status. So once I copied into the data frame, because I don't really want to mess with the original data, hence I created one copy of that. You can see that once I gather the dimensions of the dataset, there are 220,320 rows and 55 columns, where the first column is basically just an unnamed column, which is basically an index of the data. Then you have the timestamp values of in 2018 and all these sensor values. In the end, you have the machine status. So over here, I just printed the head and tail, showcasing the first 10 and the last 10 values of the entire data set. The initial task, as you know, would be to visualize the data, get a better understanding of the data. So I'm just trying to gather more understanding over here by printing the columns and checking all the relevant information that I can gather. Then I print the rows index and gather some more information about the column types and the null values. So as you can see over here, I have all these input sensor values, which are most of them are non-null, or at least all of them are non-null. Timestamp is of type data type object, and most of them have float 64 as the data type. So you can see we have 51 sensor values. You might see certain anomaly over here. We will go into this in detail, but as of now, you can see that we have 220,320 columns, so 320 rows for this kind of data. Let me go back to the other file as part of system maintenance. We have this extract, transform, and load. So we extracted all the data. It was gathered from a CSV file. It was already structured. But as you can see, now let me take a deeper dive into the data. This function I'm printing over here is basically used to print all the null count values and then iterate over them. So this gives me a sum of all the null values that are existing in the data set. Over here, we use a describe function where we are trying to assess all the unique values, drop frequency, mean, median, mode, basically gathering some more statistics related to the data. I want you to visualize the data really well in order to get in-depth understanding. So you can see that I created histograms for all the sensor values changing with respect to um, specific x-axis, and then as we go along we have this, I created a scatter plot where I wanted to see if there is any kind of correlation that would exist between sensor value number one and the machine status. I just wanted to get a grasp of how the machine status is varied. So you can see it's pretty random that it's pretty random at least at this point that you can see we have normal values where the machine is operating at normal functionality. Then you have the broken and the recovering status. So I printed all the unique values and the counts pertaining to normal, recovering, and broken. And now, since we already printed this, but I just wanted to print the data type where I know that the timestamp is of data type object, unnamed is just an index of integer, and then we have the float values, decimal values over here, and the machine status is the object. So I import the Seaborn library in order to get a plot of a better visualization of the machine status. And I wanted to print one or two random sensor values. As you can see over here, I printed sensor 1 and sensor 2. It's pretty random and the data is pretty skewed up over here. Now this was a part of extract, transform, and load. Let me go into, all right, let's take feature engineering. So as part of feature engineering, now that we have visualized the data, gotten a better understanding of the data, the next step basically is to take a deeper dive into doing some sort of feature engineering. So as you could see, if I go back to my data, you can see that sensor 15 has a null data set. It doesn't have any sensor values, and hence we know that it won't have any effect on the outcome. So the first thing I wanted to do was I wanted to drop sensor 15 because it has only null values. And then since unnamed index was not of any purpose to me, so I deleted that and then used the timestamp as the index over here. So you can see that I converted the time into an index, which makes it very easy to call out any time value and then have greater granularity in the data. So I deleted the timestamp as well, and now you can see this is my updated data, and I do have an index over here just for just for additional column set, which I can later use, or it might not be useful. Now you can see that I can directly call data frame with a 2018 as the attribute, and then you can see that I get all the sensor values which are captured in that period of 2018. There won't be 2017 or 2016 or even 2019, which I don't think exists. But now I wanted to tackle one more case. I saw that there were a lot of missing values, as you can see from the above from the above sensor values that I gathered. So the next thing I wanted to do was I wanted to fill it with a method called fill_na. So I'm trying to fill all the null sensor values, NaN values, using the ffill method over here. It really helped me in increasing the accuracy of the model. You can have different ways, like using either the mean, median, mode. You can use any of those values, but I wanted to use this fill_na function. And now, at the same time, as part of the feature transformation, since I knew that the machine output, the machine status is normal, broken, or recovering, I wanted to use this sklearn library and import label encoder in order to encode that machine status into numerical feature vector as 0, 1, and 2, where 0 implies that the machine status was broken, 1, that it was working as normal functionality, and 2, that it was in a recovery mode. Now, let's directly go to model evaluate. Definition and train would obviously come into the picture as we go along the code as well. So let me go down. Yeah, I believe so. I've already showed you all the data visualization stuff, and at the same time I've shown you the data set, how I have transformed that data set. And now, from here onwards, now you can see that I'm just printing the index with month greater than 4, less than 5, in order to just see how the sensor values are really varying over time. And you can see that it's pretty random. It's pretty hard to judge from this kind of data how the machine status would be varying with respect to or in correlation with all these 51 sensor values. And I showed you that we used fill NA to fill all the missing values and use the label encoder in order to um, transform the machine status into numerical feature vector. Now let's start off with the model definition and begin with modeling the data. So I use x and y as two variables. X gets all the data frame values into it. We copy all the data frame values into the x variable, and y variable specifically contains machine status. Hence, y is my target variable. So if you print y.head, which is kind of giving you the top 5 values existing in the vibe data frame, you can see that all of them have the machine status as 1. Now I also wanted to print x.head, basically x values, just to see all the data that I have extracted from the data frame. So it has 5 rows and 53 columns, as very clearly visible over here. We convert that into NumPy array, ND array vectors. X data gets x dot values, y data get y dot values. So you can see we have this updated x data as the vector and as a matrix, and y data as this machine status vector. Now, since the output can vary 0, 1, or 2, where 0 and 2 are technically referred to as the machine failure, right? Because either it's recovering, a recovery or broken can be identified as machine failure, where it's not operating according to its intended purpose. So it kind of acts like a binomial classification, a binary classifier, and hence I thought of using a logistic regression model, where 0 and 2 refer to as machine failure, and 1 is the machine working as a normal functionality. So we use a 70-30 training test split with a random state of 42. I did some iterations in order to see how I can increase the accuracy of the model, and then I ran this code using the logistic regression, using the 70-30 data set, and eventually predicted the y-pred value on that 30% of that test data. So as you can see, now moving on to the evaluation, you can see that I printed the confusion matrix, where 1, as you saw, was the machine working at normal functionality, and 2 was basically implying that it's not functioning properly. So this is the confusion matrix, as you can see over here. I wanted to get an accurate measure of how well I performed by changing these hyperparameters, modifying and tuning them, and at the same time using this 70-30 split. So eventually it turned out that I got a 99.7% accuracy with this kind of logistic regression model as part of this binary classification. In order to get some more insight into the classification approach that I had, I used a classification report in order to have a better visualization. So you can see I copied that and transposed it in order to have a better visualization of the F1 score, precision, recall, and support. Now, as you can see, we had really high accuracy, and it turns out that the model performed really well. Now, I wanted to print out the predicted value and the test value. It doesn't really give a whole lot of information over here, as the accuracy measure was very clear in terms of what I wanted to show here. But I could easily gather that it's working at a pretty high accuracy. And now I wanted to show or showcase the time corresponding to that predicted anomaly, because the output should be a date and time value when which the user would be notified when the y-pred, or in this case the predicted value, was a failure in the machine status. So whenever you encounter a sensor data which correlated to a machine status as recovering or having an abnormal behavior, I saved all those downtimes in a timestamp format and saved it to a file, which really helped me in gathering all that information related to the data. And then eventually I saved that classification report into a CSV file. That classification report is basically which I just showed you as part of the output metric over here.